Okay, yeah. I was afraid that the batteries died, but everything's fine. Hello, welcome to the last lecture for this year. And today's lecture will probably be a bit shorter than normal because it will be a good break over the holidays to finish the chapter and then start with the next chapter next year. So we are going to finish the chapter 4 today. And last week we talked about Pollard's algorithm, which was this algorithm where you play around a bit with Fermat's last theorem, and in the end you find a factor of a non-prime number. And the same thing we will do today, but with elliptic curves. So the idea of Pollard's algorithm was the following. The idea was Z mod P Z star, so just the units, is a group of order P minus 1. So if we have that P minus 1 divides some K, then in that group A to the K is equal to 1, mod P. So now we want to replace this by something with elliptic curves. Namely, so we take an elliptic curve, or either an elliptic curve that is already defined over Fp, or we take an elliptic curve and look at it modulo P, and then we look at the Fp rational points. So instead of looking at this, we look at this, and instead of looking at numbers A, we look at points P. So we replace this by this, and A by P. And raising to K, A raising to K by P adding to itself K times. So let me write down Lensstraw's algorithm, and then we will look at it and find out why it's useful, or why it gives us factorizations of numbers. So what we're given is only the number n, where we already know that it has factors and it's not a prime number. First we check that 6 is not a factor, and yeah, it's equal to 1, and that n is not some m to some power r. So this is easy to check, so we can just check this up front. And well, if this is not 1, then we found a factor, and if this is m to the r, then we also found a factor. So let's just assume that this is the case. And then we choose random integers. B x1, xy, between 1 and n. Hi. Oh, the stream doesn't work. So we choose random integers b, x1, y1, and we want to construct a curve with a point on it. So then we define c as y1 squared minus x1 cubed minus bx1 mod n. And then we have a curve with a point. Namely, we have the curve e is y squared is equal to x cubed plus bx plus c with a point p x1 y1 on E of fp. So this is just as we define C in such a way that this curve will have this point on it. And B and x1 and y1, we just choose it randomly. Okay. Okay, and of course, since this should be a reasonable elliptic curve, we want the discriminant not to have common divisors with n. And if so, of course, we found a factor. And if this is n, then we have to just choose new b, x1, and y1. If it's n, start over with step 2. Okay. And now we do basically the same thing as in Pollard's algorithm. We take a test number k that should have many small prime factors. For example, we take the least common multiple of some first numbers. It should just have many small prime factors. Should have many small prime factors. No, I need one more line, but okay. And then we compute k times this p. Which will have coordinates ak over dk squared, dk over dk cubed. And as we also did in Pollard's algorithm, of course we don't add p to itself just k times iteratively. We decompose it binary and then just double p and double p again and write a table and then sum it up such that we only have to do log k computations, log k additions. Yeah, we have to do more computations because one addition is some more computations, but only log k additions. Okay, and now what do we get?
What is LCM in words?
Least common multiple. No. Sorry. And then we compute the GCD of dk and n. If we have a factor, then we're done. If it's 1, either increase k or start again with step 2. So choose a new curve. Or if it's n, then we want to decrease k. So now we want to look at it and see what are the problems, when is this helpful, and when do we get a factor of n. So remember, we have n is just a number, just a big number, where we, in the best case, already know that it's not prime. We really want to find a prime factor, and we don't want to, so this is not useful for proving that a number is prime. So if we just put in any number and it is prime, then we don't get any information of this algorithm. So we start with the composite n, and then we guess some random curve, which has nothing to do with the n. It's just a helping curve with a point on it. And then we compute some multiple of a point. And in that procedure, we want to find a factor of n. So there are some different cases what can happen. So either maybe there's no problem, we get this kp, which is just has two coordinates that we can compute. And if then we compute the GCD of dk and n, and we get a factor, then everything's fine. But there's also one other possibility where we can get a factor of n. Namely, so since n is not a prime number, it can happen that it's not possible to invert numbers in z mod nz. Where's my chalk? So when we add points to different points or a point to itself, then sometimes we have to divide by numbers. And dividing by numbers is nothing else than multiplying with their inverse. So if we are in FP, this is not a problem. This is a field, and we can find inverses. But if we're in, if we compute modulo n, so if we're in z mod nz, this is not a field, so we get problems. But what can happen? So if we encounter this problem, what does it mean? Then it means we have at some step x1 minus x2 minus x1, or if we double a point, then it's y. That it's where it's the problem to divide. It's not invertible. So, but that means either the GCD of x2, well, let me write, is not invertible at some point where we add points with x coordinates x2 and x1. So either this is less than n, then we found a factor, because the GCD of this is of course a factor of n. If it's not n itself, then we found a factor. And if it's n, so if it's 1, then it's not a problem, then we can invert the number. But if it's n, which will actually happen not that often, I think, then it's just bad luck. And we have to choose a new curve. or maybe reduce k. If that happens at a very late step of adding those points, then it can also be reasonable to make k smaller and look if some of the denominators before it already give a factor. I think maybe that's also reasonable to compute the GCD of dk and n in every step where we compute those coordinates. But in general, we would have then to start with step 2 again and choose a new curve. And of course, the same thing if we have to divide by y, which happens where we double a point with y coordinate y. I had a large piece of chalk, but I lost it. Okay. Okay, and so this seems very random. Why is this actually a good algorithm? Well, if just suppose we get lucky, and in this step we find a factor that is not n and not 1, but something between 1 and n. Then this is, let me write this down. So suppose we're lucky and in step 7 we find a factor. Why does this happen? Well, at least occasionally. So for some prime p, we have that the number of fp rational points divides k. And then every element in here has order dividing k. So if we now look at k times some point, and then reduce the coordinates, which is also nothing else is, and we add it to itself k times, and it becomes the point at infinity, because for some p this divides k. Then this means nothing else than the coordinates of this resulting point have infinity as coordinates. So they have a 0 and the denominator. So they have a divisor of p, so p divides the denominator. The denominator of the coordinates. Yeah, so this is already the algorithm, and we will compute an example. It's actually not so easy to do this by hand, so we will, of course, skip some steps. And on the exercise sheet, you will have to do the algorithm once, and you will be allowed to use computers So for example, I don't know if Wolfram Alpha is able to add points maybe. And there's also Sage Online where you can compute things, but you will find that out. Oh, I'm even faster than I thought. Yeah. Okay. The example 17157 6153. Okay, so we find that this is true, so it's not a prime number, and it makes sense to look for prime factors. And what we also do, maybe with a computer, we compute square root of n, cube root of n, and so on, until then. All not integers. So step 1, with step 1 we're done. Okay, so the square root of n is about 42,000. So there is a factor that's at most 42,000. And we choose k, the least common multiple, from 1 until 17, which is this. And we hope that this has a lot of factors below 42,000, and we hope that one of those we will detect with our algorithm. Okay. So now we're at step 2. We choose random integers b, x1, and y1 between 1 and n. We take a point 2, 1. And start with b equal to 1. And this means c is -7 -2. B, so it's -9. Okay, so the curve is this one. Minus x, no, plus x, -9. And now we want to compute k times p. This is step, this is step 2 and 3 basically. Step 4 is also compute the GCD of 4 plus 27 times -9 squared. But this is 1. And n. Yeah, now we're at 5, and we want to compute k times p. So k is a large number. We write k in binary form. And log k is something like 23, so we have to compute 2p, 4p, 8p, until 2 to the 23p. We do this with our computer, and then we are able to compute k times p, which is 421401044 6, 6, 4, 3, 3, 3. Okay. What does this mean? Well, first of all, it means apparently at no point. What?
Was step 3 skipped on the...
Yeah, step 3 is basically right down the curve. Yeah, so that's why I wrote a small 3 in there. Yeah. So we have this k times p, so apparently at no point this happened. And we're at step 6 where we computed p. Yeah, maybe this is also 5 plus 6. Yeah, maybe not a good numeration. And we have our kp, and we can write it as ak over dk squared and bk over dk cubed, and compute the GCD of dk and n. Oh well, but this doesn't have a denominator, so the dk is 1. And what can we do? The factor, no, we don't have a factor. It's 1. Okay, we have to either increase k or start again at step 2. Well, k was already the least common multiple from 1 to 17, so there are really a lot of factors below 42,000. So we go back to step 2 and try again with a new curve. Oop. So let's take, so start again with a new curve. And we will try 42 because it's a nice number. Which means that c is minus 7 minus 2 times 42, and this is minus 91. And then we do the same thing again. We compute 2p, 4p, 8p, and so on. Oops, until 2 to the 23p in order to compute k times p. It's still modulo n, but now it's in the same point, but now on the new curve, on another curve. So the addition formula is different, but the modulus is the same. Then we compute k times p. And now we get that this is the point at infinity. And we look at what we did with our computer, and we see that the point of this, well, basically the last step in the computation of k, this is an integral point, so it has no denominator. The point 2 to the 23 p is integral, but the sum is the point at infinity, which means that it has a factor p in this dk. So this means when we compute the GCD of dk and n, this is between n and 1. And this is our factor. And if we look at our computer program, we see that if we look at the x-coordinate of this point, the x-coordinate of this point, and the x-coordinate of this point, and look at the difference, them and n, this will be, so this is the same as this. This is 26,927. And of course now in a computer program we would then divide n by this number and see that n is this number times this number, and then we can still find out if those are also primes, or if not, we can repeat the algorithm with those smaller primes and just do divide and conquer. Or since this number n is much larger than those two numbers, we can also maybe just use another algorithm that is not so much a probability algorithm that maybe gives an answer but maybe not, but is fast enough because there are small numbers. Yeah, I'm already finished, for today. I wanted to show you this algorithm, and in the exercises you will actually also go through this algorithm once in one exercise. And as I said, you can use any computer program you like. I think, so I usually use Sage Math, and I think if you do that online, it's called CoCalc. But you can just Google it, and then you will find it. And it's based on Python, and it's really easy. Then you can just define an elliptic curve, and then add points, and compute modulo n. And maybe it also works in Wolfram Alpha. Then that's maybe even easier to compute. And the other exercises will be easier computations. Yeah. Yeah, I think the exercise is too much to do it by hand. Well, I haven't done it myself, but it's in the book, so I think it's doable. But I think it's not doable by hand. Yeah. Okay, so thank you for your attention, and I will finish for today now already. And as I said, if you want, you can meet at 5:30 outside, and I will go to the Christmas market, and everyone is welcome to join. I will bring all my kids, so I hope that I can stay for some time, but maybe if they all get crazy, then I have to leave after half an hour. But let's hope that this will not be the case, and we can drink